You know what? I look forward to integration by parts, partially because it's something that I just added to the calculus curriculum the last time I taught it, okay? So it's relatively new. You need ink. Yeah. Don't worry. There you go. You just pull it out of this one. Oh, okay. And then throw that all away. It was cheaper to buy the pen with the replacement cartridge than the cartridge itself. I know, eh? Okay. So, integration by parts, like I said, I just added it. So officially, I've only done it once. So this could flop. Like I could just like completely, no, it'll be fine. But it is another key technique for tough integration questions. And it's a technique that undoes the product rule. So we had integration by substitution, as that was what we were working on yesterday. That undid the chain rule. This will undo the product rule. And it's really quite clever. So this is what it looks like. If you think of your product rule, you have two functions multiplied together, keep one the same, derivative of the second, plus keep the other one the same, derivative of the first. So if you would integrate both sides, okay, if you would integrate both sides of the derivative, you would get, well, here you would just get fg, because integrating a direct derivative would just be f times g. And then you would have these parts, which you could integrate separately because they're added. Now, in integration by parts, what we do is we rearrange this. We bring the fg prime by itself on one side, and then, or we leave it by itself on this side, and we move the other integral to the other side. And so what we're going to be looking for is if we recognize two things multiplied together in our integral, one of them being any function that we need to be able to take the derivative of, because on this side of the formula, there's the derivative of that function, and another function g that we could integrate, because to go from g prime back to g, and g appears twice in this formula, then we need to be able to integrate g. In addition to that, whatever we figure out f prime to be and g to be, it needs to be something we still need to integrate. Now, this is in function notations with f and g. We generally use u's and v's. So we're going to let u equal the f of x and v equal g of x. What happens to this, okay, is that, check this out, if u equals f of x, then du dx would equal f prime of x. And so using this trick that we learned in integration by substitution, we can say that du is equal to f prime of x dx. Okay? Similarly, if v is equal to g of x, then dv dx would equal g prime of x, and dv would equal g prime of x dx. That means that where we have f, we could just replace it with u. But where we have g prime of x dx, we can now replace that with dv. Where we have f prime of x dx, we can now replace that with du. and the other ones are just direct substitutions. So what is our goal with integration by parts? Okay, we want to recognize that there's two things multiplying. We want to be able to take the derivative of one of those easily, and usually we want that derivative to simplify to something that is like a constant. That's sort of usually a strategy, something that makes your equation more simple than it was originally. And secondly, you want to have a second function, which you'll call dv, that you can integrate easily and work backwards. So that's the big idea. Seeing it work is what's going to help you understand it. Hey, this is a good class to come to because this isn't in the IB, right? Awesome. Okay. So here's the integral. Initially, at this point, you might be like, oh, maybe it's substitution. And this is what was going to make integration by parts and integration by substitution a little bit harder, is now you have two options. You would use integration by substitution if you saw a function inside of another function whose derivative was present. So right here, I do see a 3x inside of e, but unfortunately, the derivative of 3x is just 3, and then we don't have any solution for this u, or for the x that's out front. So if we look at our formula, we need to decide on something for u and something for dv. So here's a possibility. You make u the x and dv the 3x dx. The other possibility is you make u the e to the 3x and the v, or the dv, the x dx. Generally speaking, we try to make the u something that when it simplifies, like in this case, if I take the derivative, du dx, it would equal 1. So du, using the thing that we learned in substitution, is basically equal to dx for substitution purposes. dv, this is an easy one to integrate, right? The integral of e to the 3x is e to the 3x, and because it would normally have a chain rule where you multiplied by 3, we have to compensate for that and divide by 3. And in integration by parts, there would be like many places where you'd have to do a plus c, and all those places where there would be different plus c's in different places would all get combined to be one big plus c. So we generally don't write plus c here, just add it at the end.
It all goes together at the end? It doesn't become like plus 2c?
No. So we just have one constant added at the end. Okay, so these were both parts that the u was easy to do the derivative. The dv was easy to integrate. And now we can write that according to the formula, the integral of x e to the 3x dx would equal u times v, which would be x times e to the 3x divided by 3, minus the integral of v du. So v in this case is e to the 3x over 3, and du is just equal to dx. Okay, doesn't seem like we got anywhere because we substituted a formula for an integral and got another integral in our answer, so we are not done solving yet. However, because du dx got rid of the variable, now this integral that's left is an integral that you can do. So if I solve for it, this would still be x e to the 3x all divided by 3 minus, and here, what's the integral of e to the 3x? It would be e to the 3x divided by 3, but because there would be a chain rule, you would have to compensate and divide by another 3. And now we can add the plus c. Let's check if we got it right. If you wanted to check if you got it right, you'd have to take the derivative. If you took the derivative, so in other words, I'm going to find y prime here. And if, by chance, it equals what was in here originally, does that make sense that we were right? Okay? And this will also help explain what integration by parts really does. Because we talked about it as sort of undoing the product rule. So can you see when I go to take the derivative that in my first term, I have a product rule? Okay? So how do we do the product rule? Well, we would keep one the same. I'm going to call the 1/3 and the x together as my first term, multiplied by the derivative of my second term. And the derivative of e to the 3x would be e to the 3x and then chain rule times 3. Plus, now keep the second one the same, e to the 3x. And the derivative of 1/3 x is just 1/3. So this part here, I'm going to put blue brackets around it. That was the derivative of that section. Then we would have a minus sign, and the derivative of e to the 3x divided by 9 will be e to the 3x divided by 9. And then there's a chain rule, the derivative of the inside function, times 3. And then, of course, the derivative of the constant will be equal to 0. Simplification-wise, can you see this 1/3 and the times by 3 cancel out? So this first term just becomes x e to the 3x. Can you see that this is 1/3 e to the 3x right here? And with this 3 and that 9, that'll be 1/3 e to the 3x. And one is positive and one is negative. And they cancel out. And we just get x e to the 3x. Beautifully, that's what we wanted to get. So for the integration by parts, if we recap what we needed to happen, we needed to recognize that there was multiplication in the original function. Once that multiplication is recognized, we need to choose one of them to be u and one of them to be dv. Generally speaking, we choose the one that's u so that when we do the derivative, it either becomes, like a very common one is if it's x, because then it becomes a constant. And that will make this part easier to integrate. The one that we choose for dv, we have to be able to integrate it in order to get the value of v. So if I, over top of here, this was u, this was v, this is the integral of v du. So here's our second example. I notice I have a product right there. 2x and cos 5x. No, this is a good thing because now we have a way of solving it. I don't see, like the derivative of cos is sine, but there's no sine present. This looks like for sure it can't be an integration by substitution. We're going to need to use integration by parts. I'm going to let u equal to 2x and dv equal to cos 5x dx. This would mean that the derivative here would be 2, which, if I rearrange this, the du is equal to 2 dx. The integral here, if you were integrating cos, positive sign or negative sign? And because it would be a chain rule where you'd have to multiply by 5, when you integrate, you're going to have to divide by 5. And so the integral of 2x cos 5x dx is going to equal u times v. U is 2x, v is sine 5x over 5, minus the integral of v, sine 5x over 5, times by du, which is 2 dx. So here I have 2x sine 5x all over 5. Can you see on this one that I could bring both the 2 and the 5 out in front as 2/5? And then what's the integral of sine 5x? Positive or negative cos? Negative cos. Because the derivative of cos is negative sine, so if we just have a sine, it will be negative cos. It'll be a 5x, but because of the chain rule, we'd have to divide by 5 plus c. Negative times a negative, that will make this positive. 2 cos 5x all over 25 plus c. Well, we were taking derivatives of product rules all the time. And when you do the rewind. When you take the derivative of the product rule, you always have something plus something. So integration by parts says if you want to integrate what is essentially part of an answer of the product rule, you would need to have something compensate or erase out the other part. So if we did the derivative of this, the first part of the derivative would match up perfectly with 2x cos 5x that we wanted. Okay? Can you see if you keep the 2x the same and did the derivative of sine 5x, you would get cos 5x times 5 divided by 5 cancels out, and you just get that first part. Whatever you get as the second part, you need to now get rid of. And that's what this second one is. It's the getting rid of the first one. It is crazy. It's really quite ingenious. And as I mentioned in my story the other day, working backwards is a lot harder than working forwards for many things. Mixing gravel and dirt. Yes. It's quite easy to take a pail of dirt and a pail of gravel and mix them together. I bet you could accomplish that within seconds.
Depends how big the pail is.
Yeah. But then if I said, I have another class that needs to also do this same activity next period, could you please separate the gravel back into this pail and the dirt back into this pail? That's going to take a very long time. So integration is extremely more difficult. In fact, if I pull out the calculus textbook that I used when I took calculus, there we go. And you open up the entire back cover. It has 75 shortcuts for integrals. Because you need them. It's like, oh, did you happen to get cotangent squared u inside your integral?
I hope not.
Well, that's tricky, but here's a shortcut. Like, what are some of the shortcuts that you get? Oh, did you happen to get e to the au times sine to the bu?
Yeah.
Yeah. You should see what you get.
What do you get?
You get e to the au over a squared plus b squared times a sine bu minus b cos bu
Well, of course.
plus c. Yeah, so there's only, your table of integrals is relatively short. Oh, wait for it. Sorry, it wasn't just the back cover. It had another page. I said there was about, how many did I say? About 75? Yeah. There's 120 shortcuts that you can use. No, probably not.
Probably.
Just 119 of them. Okay. Whew.
Oh, no. I've been looking at that one.
Yeah, I'm looking at it right now, too. This one's extra tricky
Factor of 1.
because there is no product.
Factor out of 1.
So we need to make u equal to something, and we need to make dv equal something. The dv, we need to make something we can integrate. The u, we need to make something that we can differentiate. I was going to, like, what is the opposite of integrate? I was going to say disintegrate. No, that's not.
Right? So factor out of 1.
We can use a 1. Where would you like to use the 1?
Right next to the 1x.
Because if you make u the 1, then dv is ln x, and you have to integrate it, which is what the whole question was to begin with, so we're back to square root.
Do that.
So, but if we make the dv 1 dx, that would mean we'd have to make the u ln x. And what happens sometimes when you try to use integration by parts is you pick parts and they don't work whatsoever. But you don't know that until you try. Okay? So we already determined that if you made u1 and dv the ln x, you have the same question that you started with before, which is really just a loop. We could do this a million times and still be like, I'm getting somewhere, but I'm back to where I started.
Let's do it.
But instead, if we make u the ln x, you know that du dx is 1 over x, or du would be 1 over x dx. And if dv was 1, then v would just be x. And something amazing is about to happen. Oh, I've been, like I said, looking forward to this all day, doing these questions. So now the integral of the natural log of x dx will equal u times v, which is x times natural log of x minus the integral of v, x, times du, gorgeous, Oh, love it. So nice. It's amazing. And so this stays x ln x. And x divided by x is just 1. That's an easy integral. Integral of 1 will just be x again. And we get plus c. That was less stressful than the previous ones? Yeah, the infinite loop, not so good. But this, so again, sometimes, and what might have been the case here is you don't know when you plug in the v du into this part right here. You're hopeful that you'll get an integral that you can do. But it's not guaranteed. It's just what you hope for. Oh. Yes. The squared is momentarily going to cause problems. Or make it even more enjoyable when we see how to do it. Okay? So we have a product. We need to make something u and something dv. So I'm going to make my u x squared and my dv sine 5x, because this is similar to what we've done in the past. But the extra squared causes us a little bit of a problem, because when we do du dx, we're going to get 2x, and so du is 2x dx. Okay? And we can integrate this. Integral will be positive or negative cos? Negative cos 5x, and because of a chain rule, we have to undo the chain rule, so we need to divide by 5. And so at this moment, when we write it out, x squared sine 5x dx equals u x squared times v, negative cos 5x divided by 5, minus the integral, and we have v, negative cos 5x divided by 5, times by 2x dx. Uh-oh. Why is it uh-oh? Because the integral inside is not one that's easy to do. Unless you use integration by parts again. Okay? So I'm going to say this is equal to, I'm going to rewrite this as negative x squared cos 5x over 5 minus, and I'm going to take out the, how do I want, I'm going to take out the minus sign to make it plus, and I'm going to take out the fifth. And you might be asking, why would you take out the fifth and not also the 2? Because I could take the 2 out as well. Does anybody know why I might want to just take out the fifth and leave the 2x cos 5x? A little bit of dark magic. Right, we could let 2x equal to the u and this equal to dv. But there's a specific reason. You might have to go back in time like 12 minutes and 40 seconds to figure out the specific reason I left it as 2x cos 5x.
Not only are we expected to calculus, we're expected to time travel.
Yes, time travel is going to be an essential for this one. Since you've been taking notes for the last half hour, going a little back in your notes would be approximately 12 minutes and 50 seconds.
We already did this one.
We already did this one. We did 2x cos 5x 12 minutes. Oh, now it's probably 13 minutes and 15 seconds ago. So we would get 1/5, and then here I'm going to set a big set of brackets. I'm going to go back to that question not too long ago right here. I'd be like, oh, this was the answer. Yeah, edit. Copy. You should be able to just click on the top corner of your notes. It should work. Paste. And then plus C. Now, most of the time, you wouldn't recognize you did it 12 minutes and 50 seconds ago, just like you didn't recognize you did it 12 minutes and 50 seconds ago. And so some integration by parts just need to be kept doing integration by parts. When can you see that you can keep doing an integration by parts that will eventually work? Whenever the first one is a simple power rule, right? If it's x to the squared, you have to do integration by parts twice. X cubed, you would need to do integration by parts 3 times. X to the 7,
Does this next one mean we only have to do it half the time?
you have to do integration by parts 6 times. And it's important that the other part loops. So do you see how sine to the 5x would go to cos to the 5x, back to the sine to the 5x, back to the cos to the 5x, and wouldn't ever get more complicated? E to the 3x, or e to the x ones would just keep looping back to each other. So ones that loop will work well for this. Then we got more problems. Then you just have to use shortcut number 79. Or on a scale from 1 to happy, this question makes me happy. We are going to solve this question 2 ways. First way, integration by parts. Okay? So if we let u equal x, this seems to be a good idea because then that'll just become 1. Sure enough, du dx is 1, so du is equal to dx. And if we let dv equal to, and I'll just write it as x plus 1 to the half dx, then integrating backwards, we would have to add 1 to the exponent and divide by our new exponent. Does this make our life easier? We're going to find out. So we rewrite x square root of x plus 1 dx is equal to u, which is x, times by, and are you all right if I make this 2 x plus 1 to the 3 halves divided by 3, minus the integral of v 2 x plus 1 to the 3 halves divided by 3 times by du, which happens to just be dx. And can we simplify this? Absolutely. Because this will still be 2x times x plus 1 to the 3 halves divided by 3 minus, and you would have to 2/3, add 1 to your exponent, x plus 1 to the 5 halves that we would have to divide by 5 halves plus c. So simplifying this, we would get 2x, x plus 1 to the 3 halves divided by 3 minus 4 x plus 1 to the 5 halves divided by 15 plus c. You would be expected to simplify so that you don't have a complex fraction in your final answer. So this right here is considered a complex fraction because you have a fraction within a fraction. So simplifying that so that your final answer is just a single fraction, okay? You're not required to simplify like 4/15. If it was 4/16, you could leave it instead of simplifying it to 1/4. That's fine. Okay? Now, the reason this question made me happy is because it has a secondary, beautiful solution. Here we go. We've got x times the square root of x plus 1 dx. Prepare yourself for some mathematical enjoyment. Are you ready? Okay. So, we are going to integrate this, and we are going to use substitution, even though substitution does not appear to work. Substitution, when you normally use substitution, you look for an inside function. Okay, x plus 1 is inside the function, and its derivative is present. Okay? So substitution would say we let u equal an inside function, x plus 1. Then the derivative, du dx, would just equal 1, so du is equal to dx. But under our normal substitution rules, we have a problem. Can you see that the x plus 1 would get replaced with the u? The dx would get replaced with the du. What's the problem? Nothing replaces the x. Right? Oops. Wait for it. Could I do that? If u is equal to x plus 1, I just move the 1 to the other side, and that means that x is equal to u minus 1. And so my integration. And once you get to university calculus, they will give you some very clever substitutions like this, where you have to be creative to make the substitution work. So instead of x, I can write u minus 1. Instead of square root of x plus 1, I would just have square root of u. And instead of dx, I would have du. If this u to the half I distribute, I would get u to the half times u to the 3 halves. U to the half times minus 1 would be minus u to the half du. And now I have something that's easy to integrate. No chain rules, no substitution, no integration by parts. The integration of this would just be add 1 to the exponent and divide. Add 1 to your exponent. And divide. Substituting back in. What did u equal? X plus 1. What did u equal? I'll move the 2 up to the front. Do-do-do-do. Okay. And this is another way, and these answers are very different, but also the same. Isn't that crazy? Yeah, you all nod, like, sort of like, yes, this is the proper time to nod. I have no idea what's going on. Very nice. Okay, so what's our plan coming up? Integrals quiz on Friday. Okay? That integrals quiz on Friday goes up to and includes integration by parts, which we have now finished. What we're going to do for the last 25 minutes is I'm going to hand out to you a large integral that's basically worksheets for the entire unit. And so the quiz will go up to the integration by parts, which is in the worksheet number 3. Worksheet number 1 is your basic integrals. Hey.